Welcome everyone. Today we're going to start talking about the topic of partial fractions. And as we're going to see, this is a technique that we can use to kind of split apart rational functions. And rational functions are just kind of an example is right here. A polynomial divided by another polynomial. And what this partial fractions technique is going to help us do is it's going to take this complicated looking function and it's going to allow us to kind of break it apart into kind of easier pieces. And that's what we're seeing here. We have one fraction here, another fraction here, but each of these is kind of, it's simpler. And as we're going to see, these are going to be a whole bunch easier to integrate as compared to our original function. So when you kind of look at this equation, so far in the past, we've probably worked with things like this, and when you're looking, it feels like you want to just do the subtraction, you want to do the addition. And the way we would do this, so let's suppose that we were going to start with this. Let's suppose that we started with these two fractions and we were subtracting here. How would we do that? Well, we would find a common denominator and do the subtraction. And that would give us our rational function here. And what we're going to see with partial fractions is it's kind of like the opposite of that. Instead of finding a common denominator and combining the fractions, we're going to somehow be able to split up, be able to factor the denominator and split up our fraction into many smaller fractions. So partial fractions is basically kind of undoing the common denominator work that we would be normally interested in. Now, why is this going to be helpful? Well, we'll kind of see more examples in a bit, but like we said, this function as it is written is going to be very difficult to integrate, whereas these functions are going to be much easier to integrate. So that's where partial fractions is really going to shine, is helping us integrate these more complicated rational functions. All right, so how is this process going to work? So let's look at the partial fraction decomposition. And this is basically most of what we need to know for this topic. So how does it start? Well, we start by looking at our denominator. And we start by factoring our denominator. So that's kind of the key thing here, is partial fractions really comes down to being able to factor. And what we're going to do is we're going to look at each factor in our denominator, and we're going to classify it in one of these four categories. And it's these four categories that tell us how to write out our partial fraction decomposition. All right, so if we factor our denominator and we see a term like ax plus b, where a and b are just constants, this is a linear term, and there's an exponent of 1, so we say it's a linear term with multiplicity 1. It shows up in our denominator just once. And so if we see something like that in our denominator, in our partial fraction decomposition, when we break this rational function up into many smaller fractions, we're going to write something of this form. We're going to write capital A over ax plus b. So capital A over our linear term. And here, A is just we call A a coefficient. So this is going to be something that we need to figure out. It's going to be a constant. Let's see what happens in the second case here. This is where we have a linear term, ax plus b, but now it shows up more than once. So we call that a linear term with multiplicity n, or with repeated multiplicity. But basically what we do is we start off much the same way as the previous one. So we start off with the term a1 over ax plus b, our linear term, and then we just repeat it over and over, all the while increasing the exponent until we get to however many copies there were. So we repeat this until we have n fractions, because our linear term here is being repeated n times. And then the only thing to notice here is that the exponents on these denominator terms, they're not staying the same. They're going up by 1 each time. So the power on this first term is 1, power on the second term is a 2, and then if we had a third term, it would be 3. And we keep doing that, increasing the power up until we get to however many, n is. And potentially all of these coefficients could be different. So we're calling them A1, A2 up through AN, and they could all be different, and we would have to go through and find them. So we would have to find those, and we're going to see how to do that in a few examples. Right now we're just seeing how do we actually kind of get the format for our partial fraction decomposition. The third case is if we have a quadratic term that can't be factored anymore, and we call that irreducible. So this is something like ax squared plus bx plus c. Sometimes you can factor these quadratics down, but if you can't, if you get stuck, if you can't factor it any further, we call it an irreducible. And so we have the possibility where we have an irreducible quadratic in our denominator, and it only shows up once. And in that case, we still break our fraction apart. And here we have a little bit more, though. So the format for if we see an irreducible quadratic, it's ax plus b over ax squared plus bx plus c. So there's a little bit more here than just the linear term. So in this case, a and b are coefficients. They're just constants that we'll end up having to find. And then the fourth possible case is if we have an irreducible quadratic and it's repeated n times. So it has a multiplicity of n. And much the same way that we did with the linear term, we just kind of start off how we would start off for an irreducible quadratic, but then we increase the power on our denominator by 1 up until we get to n fractions. So if it's a multiplicity n, we're going to end up with n fractions here. And each kind of fraction we introduce here, we're going up by a power of 1. So the denominator on the first fraction is has a power of 1. The denominator in the second fraction has a power of 2. If there was a third fraction, we would have a power of 3, and we would keep going however many fractions we would need until we get to power n. And then we have all these new coefficients, a1, b1, and then in our second fraction we have a2, b2. Those could be different. And then if we had a third fraction, we'd have a3, b3. So we're going to end up with a whole bunch of coefficients here. So all of them are going to be coefficients. They might all be different, and we'll have to find them all. So we're going to see how all of this works. So this will be a nice reference table for you to kind of refer back to as we're going through this section. So let's see how this is going to work. So let's look at example 1. And we're going to, in this example, we're given a few functions, and we're going to write out the form for our partial fraction decomposition, but we're not going to determine the numerical value of the coefficients. We're just trying this out. So we're just going to write the format for our partial fraction decomposition. We'll see how to find the coefficients in a little bit. All right, so let's start with this first one. We have 2x plus 5 over x minus 1 times 3x plus 4. So we have a rational function here. And I think this is one. Yeah, it's right here. So we kind of already know what the partial fraction is going to look like. But let's write out just the general form for the partial fraction decomposition. So the denominator here is nice and factored already for us. So let's look at the first linear term that we see. Well, the first term that we see, and it's linear. So we're going to make a fraction a over x minus 1. So our first linear term is x minus 1. We make a fraction with that in the denominator, and then we get a constant or a coefficient a in the numerator there. Then we go on, and we see another different linear term, so 3x plus 4. So we're going to make another fraction, 3x plus 4, and then we'll put a different constant in the top. Call that one b. And there we go. That's the format for that's the form for our partial fraction decomposition for this rational function. So you can see each linear term in the denominator kind of gets its own separate fraction here. And a and b generally are constants that we have to find out, and we'll see how to do that in a little bit. All right, let's try the next one. So in this one, we have the fraction 3x squared over 2x plus 1 times x plus 1 cubed. So when we look at this, we have a linear term here. We have a linear term here, but this one's being repeated 3 times. So let's see how this is going to work out. So the first one, let's start with our easy linear term. Just happens once, so 2x plus 1. So that's going to get its own fraction, a over 2x plus 1. And now this linear term happens 3 times, so there's going to be 3 separate fractions kind of devoted to this linear term. And let's see how this is going to work. So let's do the first one. It's going to start off as b over x plus 1. Then we're going to have a second one, and we're going to increase the power on our denominator by 1. So in the first one, we have x plus 1. In this one, we have x plus 1 squared. And then we just do it again. So we're getting a new fraction for our x plus 1, but now this one's going to have a power of 3. So for when we have these linear terms, with repeated multiplicity, we have to handle those a little bit differently than a linear term that just happens once. So if we have a linear term that just happens once, like this 2x plus 1, it just gets its own fraction, a over 2x plus 1. But if we have a linear term that's being repeated, it's going to get 3 separate fractions devoted to that linear term. And as we write them out, we just increase the power by 1 each time. So we start with x plus 1 in our first fraction, then we do x plus 1 squared in the second, and then x plus 1 cubed in the third. And if this was, say, an x plus 1 to the fourth, well, then we would have a fourth one here. And we just keep going as necessary. And then a, b, and c, and d, those are all constants that we would eventually need to find. All right, let's try a few more. So this was just all linear. The first one here was just all linear terms. The second here was all linear, but then we had this repeated multiplicity. Let's try another one. And let's look at the function 4x cubed plus 5 over x squared times x squared plus 1. And when we look at this one has, what does it have? It has this linear term right here. So we can think of this x squared as being a linear term with multiplicity 2. So you can think of it like x times x. You can factor this one further, but it's just a linear term, x, that's repeated twice. Now, this x squared plus 1, it's a quadratic, and it's an irreducible quadratic, so you can't actually factor this any further. You can try, see how to check that later on, but for right now, this is an irreducible quadratic. So let's see what happens for the partial fraction decomposition for this whole function. So let's start with our linear term. That's generally the easier thing to start with. So this is a linear term with repeated multiplicity. So we're just going to start our fraction as a over x. And since it happens twice, we're going to do a second fraction, and we'll increase the exponent. So we'll go from x up to x squared. So this x squared here is a linear term with multiplicity 2. So we're getting two fractions that are kind of devoted to that, a over x and then b over x squared. All right, what about this x squared plus 1? That's an irreducible quadratic. So that's going to get its own fraction, put it in the denominator. And the format for an irreducible quadratic is a constant times x plus d, all in the numerator. So there's a little bit more going on here for an irreducible quadratic. So just kind of note the difference. It gets a little bit more. So it's going to be cx plus d over x squared plus 1 over our irreducible quadratic. It's not just a constant. There's more going on there. And that's just the format. So that's just the way it is. All right, let's try one more of these. We're just kind of writing out the format for our partial fraction decomposition. We'll see how to find these coefficients in a couple examples. So let's try x squared plus 12x plus 4 over x minus 2 times 4 plus x squared squared. So when we look at this, we have a linear term right here. And then we have, this is another irreducible quadratic, 4 plus x squared. Way to think of it as being irreducible, you can't factor this any further. If you tried setting this equal to 0 and solving for x, you wouldn't get a solution. So you can't break this down any further. And this is an irreducible quadratic with multiplicity 2. So this one is repeated twice. All right, so how is this going to work? Well, let's start with our linear term. So that's the easier one. So we know how that works. It's going to get its own fraction. We'll put constant a in the numerator and then just our linear term in the denominator. And then we'll go on to our next factor. Now this is a 4 plus x squared. Can't break that apart any further. And this is an irreducible quadratic, so we know it's going to have this going on in the numerator. So we'll have a bx plus c. And notice how when I'm doing these, it's just easier. You know, if we don't have that many terms, just go down the alphabet. So I'm using a, b, c, d as my constants. Here I'm just using a, b. I just go to the next letter. So I have bx plus c. However you want to label the constants is fine. You just make sure that they're kind of a distinct. So they're potentially all of these constants could be different. All right, so we have this irreducible quadratic. So we have 4 plus x squared in the denominator. That gives us a bx plus c in the numerator. That's just the format for those. Now this one it's repeated twice, so we're going to have a second fraction devoted to 4 plus x squared. And that should be a plus. Now we've we have to increase the exponent on the second one. So we increase the exponent around the whole denominator up to 2. And then this is going to get, what? dx plus e in the numerator. And there we go. So we have these two fractions because that wasn't quadratic, irreducible quadratic, that was repeated twice. So we end up with two fractions, and the exponent around the entire denominator in each of those increased by 1 each time. All right, so that's the general format. Now let's get a little practice actually seeing how to solve for these constants a, b, and if we had more, c and d, and so on. So let's try example 2. And this will just be to show that this rational function here is equal to this partial fraction decomposition. So our denominator's already factored, so that's good. The first step for how to do this is just to write the general format for our partial fraction decomposition. And I'm going to do it, give myself a little bit of room here in the middle. So I look at this, and this is the same one we did on the previous, in example 1. We did this one in example 1. So we have two linear terms. So let's take the first linear term. It gets its own fraction, a over x minus 1. Then we have a second linear term in the denominator, 3x plus 4. Everything is nice and factored here for us. So that gets its own fraction, which we'll call b over 3x plus 4. And now we actually need to figure out a and b. So this is where a little bit of algebra is going to come in. We're going to have to solve some equations. All right, so this is the first step, is just to write the general format for the partial fraction decomposition. And to simplify things, to help us kind of get rid of the fractions here, we're going to multiply both sides of this equation by this denominator on the left. So we're going to take everything over here, and we're going to multiply it by x minus 1 times 3x plus 4. And we're going to do that exact same thing on the right. So we're going to multiply everything on the right by that x minus 1 times 3x plus 4. And we're going to get a lot of canceling here. So on the left, what's going to happen? Well, the x minus 1 here is going to cancel there. The 3x plus 4 is going to cancel here. So that's just going to leave us with 2x plus 5. Very nice. And then we're going to distribute. We're going to distribute this x minus 1 times 3x plus 4. We're going to distribute that whole thing to the first fraction here. And when we do that, the x minus 1s are going to cancel. So we're going to be left with a times 3x plus 4. Well, for the next thing, we're going to take this entire term and we have to distribute it to our other fraction. So we're going to, let's use red there. So we're going to have to distribute that to this other fraction with b. And so what's going to happen here is we have x minus 1 times 3x plus 4. That 3x plus 4 is going to cancel with the term in the denominator. And so we're going to be left with b times x minus 1. All right, so we have this equation now. 2x plus 5 is equal to a times 3x plus 4 plus b times x minus 1. And this equation is going to work for all x values. So we want to figure out a and b. And so the strategy we're going to use for this is to pick a few x terms and plug them in. And that's going to simplify this equation down for us. So let's try, we're going to look at our linear terms here. So let's try, we look at this first one, x minus 1. We're going to use x equals 1. And why do we do that? Let's plug x equals 1 into this equation. So when we do that on the left, what do we get? We get 2 times 1 plus 5. That's 7. What do we get when we plug x equals 1 in here? We get 3 times 1 plus 4. That's also 7. And then when we plug the 1 in here, we get 1 minus 1 is 0. So that's going to get rid of this whole second piece over here on the right. And so we end up, if we plug in x equals 1 into this equation here, so we're always going to be kind of referring back to this equation, it gives us this nice little equation, and this is going to be much easier to solve for a. And actually, we can just do it. We get a is equal to 1. Nice. All right, let's try another x value. What should we pick? And we have this other linear term here. And we saw what happened with the x equals 1. If we kind of solve this linear term, set it equal to 0, and solve for x, we're going to get some nice canceling. So that's what we're going to do here. We're going to look at this linear term, which is 3x plus 4, and let's just figure out what x value would make that 0. And it would be negative 4/3. We don't necessarily have to do that. If we wanted to, we could use x equals 0. That's also always a good choice because x equals 0 is just easy to plug in. But let's use this one. We'll get the same result regardless. So we're going to plug in. What do we get on the left-hand side? So we're going to get negative 8 over 3 plus 5. And that's going to be, what, 7 over 3? We take this negative 4/3, plug it in to this 3x plus 4. That's going to give us 0. So this whole a term is just going to be 0 because this 3x plus 4 becomes 0. And then what happens when we plug it in over here? Well, we're going to have b, and negative 4/3 minus 1, that's negative 7/3. And so this equation is not too bad to solve. We have 7/3 equal to b times negative 1 times 7/3. Divide both sides by 7/3, and we end up with b is equal to negative 1. Do a little bit of work there. And so what did we find? We found, going back to our original decomposition, we found that our a coefficient was 1 and our b coefficient was negative 1. And that's exactly what we have here. So this is kind of matching these up. We're seeing here that a is equal to 1. And we're seeing that b is equal to negative 1. And we're subtracting there. So our decomposition here actually does match up with what we expected. So we wrote the general format, a over x minus 1 plus b over 3x plus 4. And then if we actually were to plug in this a value into here and this b value into here, we would have what we wanted to show. All right, so let's try one where we don't know the answer ahead of time. Let's try example 3, where we're going to find the partial fraction decomposition of the rational function 1 over x squared minus 25. So let's start with this rational function, and now notice that it's not necessarily factored, and we actually can factor this denominator down a bit. So it factors, it's not an irreducible quadratic. You can actually factor this one down. We could go a little further with this. So it factors into x minus 5 times x plus 5. And now we see that it's just two linear terms that are being multiplied together. So step 1 here is to factor. Step 2 is now let's write down our partial fraction form. All right, so let's start with the first linear term that we wrote. That's going to get its own fraction, a over x minus 5. Then we go to our second linear term, and that's going to get its own fraction. And now it's up to us to figure out what a and b are going to be. So let's try and find a and b. And let's see here. Well, let's take this equation. Just kind of rewrite it, just because we're going to be doing some work. And what did we do last time? Well, we took this denominator on the left and we multiplied both sides of our equation by it. So we're going to multiply both sides of our equation by x minus 5 times x plus 5. Now, why do we do that? Well, it's just helping us get rid of the fractions so that we can just have a nice equation to work with as we solve for a and b. And on the left, everything's just going to cancel. So x minus 5 here is going to cancel that x minus 5. X plus 5 here is going to cancel that one. Now on the right, we're going to take this term that we're multiplying in, and we're going to distribute it to both the a and the b fraction here. When we multiply that into our a fraction, the x minus 5 here is going to cancel with this x minus 5 here. So we're going to be left with just an a, and then the x plus 5 doesn't get canceled off. So we're going to have an x plus 5 here. And on the left, what do we have? Everything canceled, so we're just going to have a 1. Keep going. Now we're going to take this x minus 5 times x plus 5, and we're going to multiply it into this b fraction. And here we have an x plus 5 in the denominator. We're multiplying in an x plus 5, so those are going to cancel. So what we're left with then is b times x minus 5. And now we just have a nice equation, 2 linear terms. So let's just plug in some x values and see how this simplifies down. So let's start with x plus 5. Let's find the corresponding x value that would make that 0. And what it is x equal to negative 5. So we're going to use negative 5 because that's going to make this linear term 0, which is just going to cancel off this whole first part. And then it'll just give us something to work with over here. So when we plug it in, what do we get? We get the equation 1 is equal to, now we're plugging negative 5 in for x, so this negative 5 plus 5, that's just going to be 0, so this whole first part is just going to be canceled out. But then we're going to have b, we don't know what b is, and then we're going to have a negative 5 minus 5, so that's just negative 10. Divide both sides by negative 10, and that tells us what b is equal to, negative 1 over 10. Nice. All right, let's try another x value. So we found one of our constants. Now we need to figure out a. So it'd be really nice if we could figure out an x value that would cancel this off. And looking at our linear term, we can do it. Plug in 5. 5 minus 5 would do it. That would cancel this off. So we're going to use x equals 5. We're going to plug it into this equation here. We'll get a 1 on the left. And then when we plug in x equals 5, we don't know what a is. We're going to get 5 plus 5 here, so that's 10. And then we're going to have plus b, but then plugging 5 in right here, we get 5 minus 5 is 0. anything times 0 is 0. So this whole second part is going to be just canceled off because it's just multiplication by 0. So our equation simplifies. So when x is equal to 5, our equation simplifies down to 1 equal to a times 10. So it simplifies down a nice bunch there, and just divide both sides by 10 to figure out a. So a is 1 over 10. And to actually answer the question then, we just have to go through and take these a and b values and plug them into our form here. So what do we end up with? And the only thing you need to be careful of here is just make sure you're plugging things into the right order. So a is equal to 1 over 10. Let's make sure we plug that in for a. So we're going to get 1 over 10 divided by x minus 5 plus, and then the next one is b. So b was negative 1 over 10, so negative 1 over 10 up there, all over x plus 5. And so there's our partial fraction decomposition, where we actually not only got the form, but we actually found the coefficients as well. All right, so we're going to stop there for today. Next time, we're just going to look at some more examples, things where we might have linear repeated terms, maybe some irreducible quadratics where we go through this procedure of finding the coefficients a and b. So really what we saw in example 3 here is just two distinct linear terms. Same thing in example 2, two distinct linear terms. So next time we'll see how do we find the coefficients if we have some repeated terms, maybe some irreducible quadratics. Similar strategies, but we'll try a few more things out. All right, so we'll see you all then with more partial fractions, more fun algebra. Bye-bye.